We saw an example of a second order linear differential equation that had the circuits problem that we couldn't solve because it was second order. And then so we broke that up into a couple of first order differential equations. But now with the higher order differential equation, we should be able to solve for this. So our DE is going to look like, in general, we'll have constant coefficients, so it's going to be some constant times a times y double prime, another constant times y prime, another constant times y. And since for now we're dealing with homogeneous differential equations, we'll set it equal to 0. And the way we're going to do this is we're going to start by assuming, which is what we've done before, assume that your solution's e to some power, e to the mx. So that's what we'll start with, and then we'll see what we get. And so if this is your exponential function, this is your possible solution, we need to put in the values in for, we need to find y double prime and y prime. So we'll find y prime first, and we'll do y double prime. And then we'll put it into the original differential equation to see what we get. So into the original differential equation to see what we get a m squared e to the mx plus b m e to the mx plus c e to the mx equals 0. And we're interested in solving for m in this case, and we see that there's an e to the mx associated with all of them, so e to the mx, and we're going to get a m squared plus b m plus c equal to 0. And we notice that we are interested in solving for m. We notice that we have a quadratic equation here in terms of m. E to the mx will never be equal to 0 regardless of what e is equal to, or m, regardless of what m is equal to. And we are interested in finding m, and so we get a quadratic equation. And so this quadratic equation has a special name, and I'll let you know as soon as I remember it, because I can't remember right now. Auxiliary, maybe? What? Maybe. Characteristic, or auxiliary. Yeah, there you go. So this is called a characteristic or auxiliary equation. And this equation will help us find our m's. Now, from algebra, you guys took algebra before, haven't you? Oh man, I went too far. Oh, what just happened? Let's just skip this section. What if I skip it and you still be responsible for it? All right. So back to your algebra days. When we ran into an equation like this, we used that thing, quadratic formula. And we know that if we use that thing, quadratic formula, then there's a couple of possibilities, actually 3 possibilities that will come up, right, depending on what's under the square root. Remember the discriminant for your quadratic formula? So we have essentially 3 cases. How come it's not blue? Slash auxiliary. It keeps moving. Why? Am I blue now? So we have 3 cases depending on our discriminant. Remember the discriminant? B squared minus 4ac, or is it b squared 2a, or negative b squared plus or minus that thing inside of the parenthesis or inside of the square root. What is that? Discriminant. So if your discriminant is positive, all right. Maybe I should just. If your discriminant is positive, then you have this thing under the square root. Remember, outside of the square root, there's a plus and minus. So if it's positive, then you'll have 2 solutions. There's a possibility that, let me try to match up with my notes here. Case 2, 1 real root. If you have a case where the discriminant's equal to 0, then you only have 1 root, right? Because it'll be negative b plus or minus 0 divided by 2a, so it's negative b over 2a. That's just 1 root. And then it has multiplicity too, but essentially it's 1 real root. And then the last case is that if it's negative, you get a negative under a square root that gives you some complex numbers. You get 2 complex. A complex conjugate is a pair of numbers that have the same real part and same imaginary part, except the imaginary part is a negative. So example would be 1 plus 2i and 1 minus 2i. So these are complex conjugates to say that you have the same real part and the same imaginary part, except the signs are different. So you get a pair of them, and that's what's going to happen if the discriminant is a negative. So we will deal with each of these by just doing some examples. Okay? All right, so let's take our case 1. See if there's an example for that. So let's take a look at this. This is a case 1 example. And we're going to approach this by assuming that our solution is e to the mx. So assume that y is equal to e to the mx. And we saw, after a while, we can skip over a couple of these steps. But I think for a little while, you should write them out. And so we want a couple of derivatives here. And then we're going to plug in these derivatives into the original equation, the derivative and the original assumption into the equation. We're going to get m squared e to the mx, that's y double prime, minus y prime is m e to the mx, minus 6 times y e to the mx is equal to 0. So this is our equation now, where we're trying to solve for m. And like we did before in the example, we're going to take out an e to the mx and assume that it's never going to be equal to 0. So we can really just cross that out. But more importantly, what we have left here is a quadratic equation. And if you look at the quadratic equation, our characteristic or auxiliary equation compared to the original differential equation, you see that the coefficients are the same. So it's always going to be like that. So these are some of the steps that we'll eventually skip later on, but it'd be good to see the process for the first couple of times. And so I think we can factor this, right? 2 and 3 or something. M minus 3, M plus 2 equals 0. And then you're going to get, we'll call it M1 and M2. We'll get negative 2 and positive 3 to be our solutions. Yeah, so your solution is going to be, well, we'll call it y1 and y2 maybe. Y1 is equal to e to the minus 2x. Remember m, x, so m is equal to minus 2. And y2 is equal to e to the 3x. Now you can check for yourself by using the Wronskian or something that these two are actually linearly independent. What? Yeah, so you're eventually going to have to write the general solution. So right now these are solutions. And you can also check that this actually works by putting it back into the original equation. But let's just say it works. Yeah? Say it again? It doesn't really matter. My tendency, and I think the program in your homework also does the lesser number first, but it's not, doesn't make a difference. And so our general solution is going to be y is equal to c1 and then y1, which is e to the minus 2x plus c2 and y2. And again, you can take that solution and put that back into the original differential equation to see that it would work. So you would do that by taking the derivative once and twice and then putting it back to the original equation and seeing that this is all going to amount to 0. Okay? Any questions? It's pretty straightforward, yeah? Maybe we'll do another example later, but let's get to the next case first. Yeah. Wronskian. All right. Our next case is when we get one real root. Let's see if we can come up with an example here. I would say maybe number 6, maybe, hopefully, we'll see. Okay. So let's again assume that our solution is going to be y is equal to e to the mx, and we'll take a couple of derivatives and put it back into the original equation. Y prime is equal to me to the mx, y double prime is equal to m squared e to the mx, and put that into here. We're going to get m squared e to the mx minus 10, and then we have m e to the mx, and then we have 25 just e to the mx equals 0. Factor out an e to the mx. You get m squared minus 10m plus 25 equals 0. And then you have your auxiliary equation without the e to the mx. And then we solve for that. You can factor that, right? It's m minus 5 twice. So we got m is equal to 5, and we only have one solution. So we got one solution, which is great. But this is a second order differential equation, so we're going to need that many, the same order as the order of the differential equation. We need that many linearly independent solutions for our fundamental set. How do you think we can find our second solution? What was our previous method? Yeah, what's that called? Reduction of order. Thank you. Reduction of order. So at the end of your notes, I added in a general derived formula for at least second order differential equations. And here it would just require you to take a look at a formula instead of the stuff that you guys did. This is kind of like the shortcut. So let's see if we can use this shortcut for our reduction of order. It's still reduction of order. So let's say we have a reduction of order formula. And let's take a look at how this works. So we identify a couple of things. We need to identify the y1. Oh, we got y1 over here. We need the p. The p, if your original differential equation is written in your second order differential equation is written in standard form, the y double prime doesn't have any coefficients aside from 1. Then you look at the coefficient of the y prime, and that's going to be your p of x. So in this case, our p of x is equal to -10. And I think that's all we need in this formula. Notice that q would normally be something that we should consider is not considered at all in this reduction of order. Yeah. So here's our formula. We have y1 and we have p, so let's try it out and see if it'll work. So to find our y2, keeps changing here. We got e to the 5x, and then now we need to integrate e to the minus the integral of -10 dx divided by e to the 5x squared dx. So we kind of need to do this first. Let's see if we could do this in a different color. Yeah. Oh, p of x comes from the original differential equation, and that's the function. In this case, it's just a number, but sometimes it could be a function. But that's the expression or the coefficient of y prime. And remember that the y double prime has to have a coefficient of 1. So if the coefficient of y double prime is not 1, then we need to divide that out, because that makes a difference. All right, so we were trying to figure this out. This is a positive 10, it turns out, right? E to the integral of 10 dx is equal to e to the 10x. Is that right? So that's what goes in the numerator. And then now let's bring it back to the actual problem. We have this is equal to e to the 5x integral. We just found out that the numerator is e to the 10x, and the denominator is e to the 5x quantity squared. That's e to the 10x again. So this is 1, and integral of 1 is what? X plus c. Now, the plus c's, I don't make maybe this argument is not convincing enough, but as you guys were working on doing your problems, you ended up calling the plus c something, 1 and 0 or something like that. But during the process, you make those arbitrary constants, or you don't even count those arbitrary constants, and then everything should still work out, because when you create your general solution, those arbitrary constants will pop up again. And so we'll ignore those arbitrary constants, and so this is what we end up having. So your second solution, y2, is going to be x e to the 5x. Keeps going over there. All right. So I think we're good. And then your general solution. Y is equal to C1 e to the 5x plus C2 x times e to the 5x. And these two fundamental solutions are actually linearly independent. One of them has an x, the other one doesn't. So you can, again, check the Wronskian. You can also take your solution and plug that back into the original differential equation to show that it actually will work when you take the two derivatives and plug it back in. Okay? So to summarize the first two cases, in nicer writing, that if you have two distinct real roots, then your solutions would just be those roots being multiplied as part of the exponential function. And then C1 times the first plus C2 times the second. Order doesn't matter. I just like to generally like the smaller number first, but it doesn't really matter. And for the second case, and regardless of what your e to the mx is going to equal to, the reduction of order will always come up with an x. So that if you have a repeated root, you have one real solution, then your general solution for your differential equation would be e to the that solution times x plus c2 times x times e to that solution times x. And so this extra x, half of you should have done this, because this is similar to the problem that you guys did in that video that you're supposed to submit. Half of you should have came up with this x as your other solution, or x times e to whatever that thing is you're working with. All right. Any questions? All right. Case 3. Yeah. Are you talking about the constants here at the final answer, or the constants that come out when you do these integrals? In the final answer? Because you're talking about a second order differential equation, so you're first of all, you want two fundamental solutions that are linearly independent. Second, when you string up your linear combination of those two fundamental solutions, you want constants there as your parameters. So when you're dealing with a second order differential equation, you should expect a two parameter family of curves. And so these parameters come out as coefficients. The superposition principle tells us that if we have n linearly independent solutions for your nth order differential equation, then your solution will have these arbitrary constants there. And those arbitrary constants, you can't assign them zeros and ones or any other number for that matter until you're going to use the initial conditions to solve for that. So the only way to get around getting rid of these constants at this point is that if you have an actual IVP, initial value problem. So you would use your initial conditions, two of them, to help solve for the two variables. Does that answer your question? More or less? Okay. Anything else? All right. So third case. So when you get complex conjugates, we have to deal with complex numbers. If you're interested in the spring semester, we can do a complex analysis group and have a little independent study class of complex analysis. I had one last semester, and it turned out, we only had like 3 people, but we met once a week and we got together and we talked about it. And what? Well, it's whatever you want it to be. Anyways, it turned out to be, for those guys, it turned out to be a 3-unit, and a couple of them had honors credit for it. But anyways, it's a like in-depth study of complex analysis. So if you've gone through a regular math curriculum here, you probably saw complex numbers when you guys were doing second order, or not second order, but quadratic functions, quadratic formulas. And then you got these imaginary numbers, and then you touched on it a little bit, but then left it aside and never saw it again. You might have seen it maybe in some of your other engineering classes where you had to deal with complex numbers. Yeah. But in general, people stay away from it. And it turns out that, unless you actually take a whole class dealing with complex numbers, you'll only see the basics of it. And so here we're going to talk about the basics of this. We're going to dig a little bit deeper than what you've done in algebra. And there might even be some things that you might have seen in Calc 2 when you guys are dealing with series. But let's talk about complex conjugates. So your complex conjugates, let's say your solution will end up being m is equal to some number. I don't want to use a or b because we're using a and b in the differential equation. So I'll use Greek letters, alpha plus or minus beta I. So this would be your solutions, or the solutions to your auxiliary equation. And then your solutions would then be y is equal to e to this thing, alpha plus or minus beta I times x. So it seems like we can think about this as having 2 solutions. One solution is y is equal to e to the alpha plus beta I. Well, I don't know. And e to the alpha minus beta I. And it turns out that we can rewrite this as e to the alpha times e to the beta I, or e to the alpha times e to the minus beta I. Oh, I forgot my x's. So that's nice. Supposed to change colors here. But the big question is, why am I not changing colors? Alpha is a real number, beta is a real number, but now I have this e to the beta I x. What is that? How should we approach this? I could just give you the formula and be done with it, or we can make it kind of fun. Let's do fun. I picked fun. All right. You guys have all taken Calc 2 and passed, maybe? Hey, serious? Series. Series. So one way to work with this is to think back in our calculus where we get to expand e to the x. Do you remember the series expansion for e to the x? If you don't, you'll need to know it in like a couple of weeks, in a month. I mean, have it memorized to heart. I could. I guess I should use n or k here. And when k is equal to 0, you have x to the 0 power, which is 1, and 0 factorial. What's 0 factorial? 1. It's not 0, it's 1. Google it. Hey Siri, what's 0 factorial? The answer is 1. Ask your own personal device. All right, when k is equal to 1, we have x to the first power divided by 1 factorial, which is again 1. And then we get the pattern for this, right? So now we're interested in looking at what happens if we put b times I. So there's a couple of things you need to know, the very basics about imaginary numbers. Is that, well, let's put it in first, and then we'll see what you really need to know for imaginary numbers. So if I put e to the beta I, and I'm going to leave the x out for now. Is it okay to leave the x out? Yeah, let's put the x in. Sorry, my for some reason I don't have very much control in this thing right now. Oh, I said I was going to put the x in. Let's put the x in. Let's squeeze the x in somewhere, maybe next to the beta. So the first one is just a constant, it's 1. The next one is beta x I. The next one is beta xi squared over 2 factorial beta xi to the third over 3 factorial beta xi. So I want to go up to 8, I think, because we can see patterns from the way we're going to split this up. For this particular example. I'm just going to stop here. I just know. All right. So I'm curious now to see what happens with the eyes. There's an eye here, and we can simplify The beta times x being squared is not going to be that big of a deal, but the I squared is something that we can probably simplify, right? What is I squared? I squared is -1. So backtrack to some more information that you should know. You should know a little bit about imaginary numbers. I to the 0 is what? 1. I to the 1 is I squared is -1. I cubed is what? Is what? Negative I, right? It's I squared times I. It's -1 times I to the 4th, negative I times I. So it's a negative I, and then you have times I. So negative times I times I. What's I times I? I times I is -1, and then you have a negative in front of that. So if you want to think about I to the 4th is I cubed times I, which is minus I times I, which is minus I times I, which is -1 times -1, which is +1. I to the 4th is 1, is basically what I'm trying to get at. Then I to the 5th is just I. So you can see that this kind of starts looping itself, and so they generate this pattern of either 1, I, -I, or -1. I probably said that in the wrong order. It's 1, then I, then -1, then -I, and then 1 again. So like the first one, technically you have b times x times I to the 0 power, and that's just 1. Yeah. So this one, we get a -1 here, right? I squared. So this would be a negative beta x squared over 2 factorial. What was I cubed again? -I, so it's -I, and then beta x cubed over 3 factorial. And then we have, what's I to the 4th? I to the 4th is just 1, right? So this is just beta x to the 4th power over 4 factorial. Okay, let's keep going. I to the 5th. Just regular I, not negative. So beta x to the 5th times I over 5 factorial. And I to the 6th, that's -I. Beta x to the 6th over 6 factorial. 7th, so we just had -I. So +1. Wait, what's to the 6th? 6 should be -1, right? Not -I. So -1. 7 would be -I. So 7 would be -I. Beta x to the 7th over 7 factorial. And then this would be, 8 would be what? +1. Okay. So there's a lot of them. What I'm interested in doing is I'm interested in collecting all the terms that have an I and all the terms that don't have an I. So if you notice something interesting about the terms that have an I versus the terms that don't have an I, the powers seem to be all even or all odds, right? So I'll go here with 1 minus beta x squared over 2 factorial plus beta x to the 4th over 4 factorial minus beta x to the 6th over 6 factorial plus beta x to the 8th over 8 factorial. Do you see a pattern? What do you think is next? So plus or minus? Minus beta x to the 10 factorial. All right, so we got the pattern for this one. Let's see if we can find the pattern for the odd powered ones. So we start off with a beta xi minus, wait, they all have i's in them, right? So I'm just going to factor out the i's from every single one of them, right? So let's start over and factor out the I, because I know that each of them is going to have a factor of I. And then let's just take a look at the numbers, or the whatever's left. Beta x minus beta x cubed over 3 factorial plus beta x to the 5th over 5 factorial. And then what's next? Beta x to the 7th over 7 factorial. And what do you think would be next? Plus or minus? Plus, it looks like it's an alternating series. Beta x to the what? 9th over 9 factorial. And then we can even go one more. It should be a minus. Okay. Now this is going to be where you go back to your Calc 2, and if you have a series, it looks like it's an alternating series. It looks like the powers match the factorial on the bottom, and you're only looking at the even numbers. Does that series look familiar? That's the cosine function. What? Let's Google it in case we don't touch it. Cosine function. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus alternating all even powers. In fact, cosine is an even function. Makes sense. Sine starts off with an x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Alternating series, only odd powers. That's just the sine and the cosine we got here, right? Now that you're convinced. Thanks, Brandon. The things that are being raised to the power is beta x. So that whole first thing in the green, highlighted in the green, It's just cosine of beta x series. It goes on forever. We've found the pattern, alternating series, all even powers. So this fits the cosine. The next one, remember that there's an I in front. I is a complex number, and it's just a constant. And then we can convince ourselves, or you can convince yourselves, that this is a sine function. Well, whenever you stop, it's an approximation, but the dot, dot, dot tells you to go forever, and then that's the exact value of the sine and the cosine. Yes? This is Euler's formula. E to the beta xi equal to this is Euler's formula. I mean, beta x, instead of beta x, you might see it as theta. So e to the theta I equals that. Yeah. So you can put specific values for theta. If theta is equal to pi, let's actually label this Euler. If you put a specific value for theta, you can put 0 in here and see what happens. You could put, values in here, but a special value is e to the pi I if you put pi in for theta. What's cosine of pi? -1. What's sine of pi? So this is another one of these formulas that people get tattoos of. Yeah. Not this one. What? There's a fundamental theorem of calculus, and if you take Calc 3 with me in a couple of years, then I show you my fundamental theorem formula tattoo suggestion. No. This, by the way, also this describes a rotation. Euler's formula can be seen as a rotation matrix. Anyways, that's a little bit of an aside. But what we do want to get is Euler's formula, and this expression that we just found. It can be something that we can put into the original differential equation, or the solution that we're looking for. Well, the thing is, complex number, you can think about complex numbers as imaginary, but they use it in real life situations. It's a real thing. They use it in physics, they use it in engineering and stuff like that. We just need to go to the complex world for a moment to solve our problem, and then we take it back to the real world and say, here's our solution with sine and cosine. We're going to be going to different worlds in this class every once in a while. So, back to our solution. Our solution is originally looking like e to the alpha times x times e to the beta I times x. So we have e to the alpha x times the cosine of beta x plus I sine beta x. Now our conjugate, e to the alpha x e to the minus beta I x, is essentially going to be the same thing. So these two sets look like they might be linearly dependent, because the only difference here is that there's a minus. So what we're going to do, instead of looking at these as a whole set of solutions, we're just going to notice that, hey, this first one, if you distribute that, you actually get two solutions right there. And then for the second one, if you distribute that, you're going to get two solutions also that are linearly dependent. I can't bring this down anymore. So what you really have here, solutions look like e to the alpha times x times cosine beta x, I e to the alpha times x times sine beta x, e to the alpha. This is the same thing. I don't know why I'm writing it again. And the next one is negative e to the alpha x sine beta x. One's positive, one's negative, but I tried to tell you in the beginning that I is an imaginary number and I is just a constant. So when you put constants in front of this, I can just kind of merge into that constant that we've been dealing with. So what are the two linearly independent solutions we have here? Now, the cosine and the sine. And again, stressing the fact that I is just a number, a constant. This is all we really care about. The e to the alpha x times cosine beta x is one of them, and then e to the alpha x times sine beta x is the other one. So those are your two linearly independent solutions. So summarizing into something that you can actually read, unlike my handwriting. The bottom line is that your two linearly independent fundamental solutions are e to the alpha x times cosine beta x is one of them, and then e to the alpha x times sine beta x is the other one. Okay? The general solution would be these two linear combinations. So there you have C1 times the first and C2 times the second. So that was a fun little detour to series. Yeah, it's fun. Actually, you need to know these series by heart. E to the x, cosine x, sine x, and then maybe the first one here, the geometric series. Because chapter 6, which will be after the second exam, will start off with series. Okay. So we haven't really done an example yet. We've done the general idea behind it. So let's actually do an example for complex conjugates. Number 9 seems to be pretty easy and straightforward, or 10, same. So the thing about this is that those results that we got, the things that I copied and pasted from the notes, those are just things that you would just memorize, remember. You don't have to go through this whole process of letting your y equal to e to the mx and then finding the auxiliary equations and stuff. I think it's good for you to do that for the first few problems that you're going to do in your homework. But from here on, I mean, from then on, starting in a couple of weeks, we're going to be uh, dealing with non-homogeneous differential equations, where the first part is to solve for the homogeneous differential equation. So we're going to fly over solving for the homogeneous because we have these three cases and we know them already. The result should be something that you should get used to quickly enough to be able to do these problems quicker than what we're doing now. All right, so here's our differential equation. We're going to start off again. We're not going to skip that many steps yet. We're going to assume that y is equal to e to the mx is our differential equation, or our solution to our differential equation. We don't have y prime, but we still have y double prime, so we're still going to need to take our steps to get to y double prime. So y double prime is going to be m squared e to the mx. So we'll take our y squared and our y, put it back into this differential equation. We have 3m squared e to the mx plus e to the mx, 0, factor out on e to the mx. And then solve for this. I can't factor this, it looks like. I mean, I can use a quadratic equation, but if we do the, bring the -1 over to the other side, take the square root, and blah, 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 we're going to get a solution. So what is it going to be? 3m squared equals -1. You can divide by 3 now. M squared equals -1/3, and then take the square root. M is equal to plus or minus the square root of 1 over 3, or whatever, however you want to write this. But in any case, oh, there's an I in here because the -1/3. So this is we have a set of complex conjugates. The alpha, if you want to try to match it up with the formula that we had in the previous page, the alpha is equal to 0 in this case, and then the beta is equal to 1 over √3. So those are our alphas and betas. And then we know that if we have a complex conjugate for our solution, we know that our two fundamental solutions, so skipping over all the steps that we just did last time and going over to our results, y sub 1 is equal to e to the 0. Let's make that clear here. So e to the 0 is equal to 1, so that's just going to be 1. And then cosine 1 over square root of 3 times x. y2 is equal to e to the 0 again, sine 1 over √3 times x. So these are your two linearly independent solutions, and then you put them as a linear combination just by putting C1 in front of the first one and C2 in front of the second one. So you get a general solution. And then that's it, right? So it seems really simple, but it came from, no, I mean, the C1, yeah, the C1 can make it positive or negative. And then you can also put this back into the original differential equation and see that this is actually going to work. We're going to find solutions for this. Okay. So, any questions? All right, let's try one that's higher order than 2. So the title of this is Homogeneous linear differential equations with constant coefficients. There's really nothing that's restricting us to just having having this as second order differential equation. So let's see if we can find one that's of a higher order differential equation, and hopefully we can factor it. Let's do number 16. As long as it has constant coefficients. So in this case, we have a third order differential equation. Y triple prime minus y is equal to 0. It's like the third derivative. Yeah, that's all it's saying. So what we're going to do is we're going to assume the same thing. We're going to assume that our solution is e to the mx, and then see where we go from there. So solution y is equal to e to the mx. We need some derivatives here. Y prime is m e to the mx. Y double prime m squared e to the mx. Y triple prime m cubed e to the mx. So you can see the pattern here also, right? It looks like the powers for your characteristic equation matches the number of derivatives in your original differential equations. That's the nice thing about having these constant coefficients. And then it's not a coincidence that this y triple prime would turn into an m cubed, and the e to the mx is something that we'll factor out, and then we have e to the mx. So we just have m to the third power minus 1. Do you remember the formula for the difference of two cubes? No. All right. Difference of two cubes, factors like that. The first one, we have m is equal to 1. That's nice and easy to remember. The second one, it's an irreducible quadratic, which means irreducible over the real numbers, which means it'll require you to do some quadratic formula thing. So if we set each of them equal to 0, we're going to get m is equal to 1 as one solution. And then we're going to get m is equal to, let's use a quadratic formula, negative b minus plus or minus the square root of b squared minus 4ac all over 2a. So that's a negative 1/2 plus or minus the square root of, I have 1 minus 4, that's negative 3, right? I guess I got my square root a little too big. So that's going to give us an imaginary number. So I have negative 1/2 plus or minus square root of 3 over 2i. So what we're going to do is we're going to piece together these solutions that we're looking for. So your solutions are supposed to be e to this m power. So coming out of this first solution, we're going to get y1 is equal to e to the 1 times x power. Now for this, since we have complex conjugates, remember that we're going to come out with two solutions. And yeah, plug it to the formula. But the two solutions that we're going to get is going to be e to the alpha. Alpha is equal to negative 1/2 in this case. So e to the negative 1/2 x times, the first one is going to have the cosine, second one is going to have the sine. So the cosine, now the sine, S-I-G-N, sine, not the S-I-N-E, sine. The sine of this angle is, it doesn't matter if it's positive, negative, we're just going to use the positive. So it's just going to be √3/2 x. And then your third solution, your second solution from the complex conjugates, and third solution overall would be the same alpha, e to the alpha x, and then this time you'll have sine, S-I-N-E, 3/2x. Okay? So your general solution will then just be a linear combination of all these fundamental solutions. Come on, Gen solution. Y is equal to C1 e to the x plus C2 e to the negative 1/2 x cosine √3/2x plus C3 e to the negative 1/2 x sine √3/2x. Bam. Okay. We all good here? I was thinking this would be easy. This was easier than the stuff that we've been doing in the past, right? Because here is something more concrete and we're getting solutions, we're getting formulas right away. And so this would be helpful. The only weird thing is the whole complex analysis stuff. Yeah, so you could do the same thing with degree 4 and 5. It all depends on the solutions for your characteristic equation. And the key is you have to be able to factor it. So if you have a 4th degree polynomial, you have to try to factor it. And the factors are real numbers or complex numbers. All right, next time.